So our next speaker will be Santosh Nagarakatte from the University of Pennsylvania, who will soon become an assistant professor in the Rutgers University starting next January. So today he's going to talk about verified LLVM, formalizing the semantics of the LLVM intermediate representation for verified program transformations.
Thanks, Chuck, for the introduction. So I'm starting as an assistant professor of computer science at Rutgers from starting January. So this is joint work with my collaborators, Jinjo Zhao, Steve Danzovic, and Milo Martin at the University of Pennsylvania. So Jinjo did most of the work for his dissertation, and he couldn't be here for various reasons. So let me start by giving you why we started this project. So we have been using LLVM for a long time, and LLVM has been an enabler for us to do lots of interesting things. So it enabled us to implement a few of the research ideas and explore it with real-world code. So in 2009, we had a paper in PLDI where we wanted to enforce memory safety for C programs. We designed the semantics of the instrumentation on the LLVM IR, and within 4 months, we could actually transform, we could implement the optimized instrumentation and experiment with real-world code. And then when we actually designed this transformation, we designed proofs for why the instrumentation is correct. Essentially, it's the specification, right? And then we had some guarantees about our instrumentation providing the right security properties we wanted to enforce. And then we asked the question, well, this is an implementation, the C++ implementation, which actually transforms code. Can we say anything about the implementation? And the implementation, there are two options. You can say, oh, well, Santosh has been writing LLVM code for a long time, and he should be doing the right thing, right? And alternatively, we can use LLVM test suite and say, oh, we passed the test suite, and we should be correct. Or you can trust our proofs, say, oh, Santosh has done the translation very well, and it should be correct. So, but it made us ask the right question. It made us ask the bigger question, can we trust the implementation of the compilers? In general, compilers are known to implement correct algorithms, well-known algorithms, which have correctness proofs. But then there are programmers who translate these algorithms into actual implementations and which work with real-world code. So, but there was a nice paper in PLDI 2011 from John Reger's group at Utah, which said compilers are not always correct. So to ascertain this, they designed a tool called Smith, which generated valid random programs, and they experimented with various compilers with these random valid programs. And to the surprise of many in the community, they found lots of bugs in many industrial strength compilers, in LLVM included. So now we have compilers which use correct algorithms, and then their implementations have bugs. So what could we do? OK, so just going back one step back, what are the kind of bugs that these guys actually found? So there are two kinds of bugs. One, you have an input, the compiler crashes. I think this is a kind of OK bug, because in the worst case, you'll not be able to compile your program. And the second kind of bug is the compiler silently generates wrong code. And this is a serious kind of bug. You don't even get a notice from the compiler saying that you're doing the wrong thing. So this is serious. What can we do? How can we ensure that the compilers are free of errors? Compiler implementations are free of errors. And that's the question we wanted to address. And there are two ways we can go about addressing this problem. One is we can build extensive test suites and develop rigorous methodologies. And in fact, there are lots of nice test suites, and it's an industry of its own. And GCC torture tests are one example. But the problem with testing is you need to come up with good coverage metrics. You need to come up with new inputs. And it's a hard thing in general. So alternatively, as an intellectual adventure, we wanted to say, let's say we write, these are correct algorithms, right? Let's say we write the specification of the algorithm, the proof of the algorithm, and also the implementation in the same system. And this is what we call the proof of system. And if we can do this, we can build a robust compiler. So the problem here is the implementation and the proof are mismatched. So can we actually build a compiler within a proof of system? And in fact, we are not the first. ComCert guys, ComCert is a verified compiler written in a proof assistant. This is from Xavier Luas' group at INRIA. They showed that for a subset of a C language, if you design your custom intermediate representations, you can actually build an end-to-end verified compiler. And they use a proof assistant called COG, which has a rich system for programming and as well as proving. And then they built OCaml bindings and used COG's extraction mechanisms to generate a compiler, which comes with a proof of correctness, and it plugs into real-world code. So the next question is, does this compiler fare better compared when evaluated with John Reger's test suite? So in fact, John Reger's group found that COMCERT is much more robust than other compilers. Like the errors they found were primarily in the parts which were not machine checked. So this provides some validity to the claim that there is a value in writing a compiler within a proof assistant, especially for critical domains where compiler correctness is such an important issue. Okay, so this was amazingly, we were extremely motivated by this fact. Now the question is, can we write LLVM within a compiler? So when we are working with LLVM, we don't have the luxury of defining our own intermediate representations and own stuff, right? So, and LLVM IR has some nice properties which I'll describe during the talk. So how can we write LLVM in the proof assistant? And can we even do it? Like when we started this project like three and a half years ago, we didn't even know we could even accomplish this and make it work with real world code. So in summary, this is like a one slide summary of the entire talk. So we have formalized the LLVM's IR syntax, semantics in the proof assistant. Then we have written verified optimizations in the proof assistant. The above, the top part is the things written in the proof assistant. And then we cannot reinvent everything, right? We need to interact with existing tools. So we have written OCaml printers and parsers so that we can actually interface with the LLVM world. So all the stuff written in the top part comes with a proof of correctness. And then we hope that there are no bugs in the printers and the parsers. We don't have any proofs of them yet. And our instrumentations actually work with real world code. So I'll describe most of this in the rest of the talk. So what are the key contributions? Okay, this seems like we have proved something in the LLVM, right? So one of the key contributions was coming up with a formal semantics of the LLVM IR. So LLVM IR right now is described in documentation. And so how do you translate English prose to formal semantics? It required a lot of reverse engineering and a lot of emails which are sent to the LLVM developers list. And I think this is one of the strengths of the community, that developers interact with you so frequently. Like we had lots of questions, and they were patient to answer some of this, and our knowledge was actually enriched by such an interaction. And it required a lot of reverse engineering and understanding the intent of the actual designers to design the IR in a particular way that they did. So the next question is, LLVM IR has unique features. Like LLVM IR is typed, even though it's not type safe, and it's SSA based. So how do you formalize the semantics of such an IR? And then LLVM has this type index undef, which makes the semantics non-deterministic. I'll describe this with an example in the rest of the talk. And how do you even formalize a non-deterministic semantics and create a refinement that can work with real world code? And then when you're designing semantics, you can always define semantics the way it's convenient to you, right? But our goal was to reason about optimizations. And we wanted to reason about all the optimizations in the LLVM suite. So we had to design semantics so that we could handle all optimizations. And we also wanted to keep in mind that the proofs are simple to write. And if the proof engineering is going to take years and years of effort to even prove just a single optimization, that's a non-starter, right? So, and then we built a set of tools to interact with LLVM. And then just to show that our semantics is useful, we write a verified version of our memory safety transformation. We write a verified version of one of the most performance critical optimizations in the LLVM suite. Okay, let me start by giving you a brief outline. So I'll give you some background on the LLVM IR and what our proof assistant is. And then I'll describe the key parts of the semantics. And there's a lot of work. If you're interested, look at our POPL 2012 paper, which formalizes semantics in much more detail. And the source codes are all available, and you can download and use it. And then I'll describe how we actually formalize the memory safety transformation and the performance critical optimization in LLVM. And then few of the lessons learned interspersed in the rest of the talk. Okay, so I've been talking about proof assistant for a while. So the proof assistant which we use is called COG. So it was developed by INRIA. So it has a core language called Galena. which is good enough to write lots of programs. And the key thing they had in mind is it's good to write proofs. So the core calculus is called calculus of inductive constructions, which is based on constructive logic. So apart from all those, the key thing is you can write specifications, programs, and proofs in the same system. And it's very expressive to do this. And then there's an extraction mechanism provided by the proof assistant, which can be used to extract programs, and you can interface with the real LLVM code. So given that this is the proof assistant we are going to use, and there's a rich support available which made us use this proof assistant. So we need to formalize LLVM. So LLVM is a big system. So when we are saying we are formalizing LLVM, what aspects are we considering? So LLVM has a set of source languages. It converts them into an intermediate representation and runs lots of optimization and analysis on the intermediate representation. And then there is a backend which converts it to target languages. And in this effort, we wanted to focus ourselves on the LLVM IR and the set of machine-independent optimizations which come with LLVM IR. Okay? So in the rest of the talk, I'll describe the semantics and the uses of the semantics. So I don't want you to understand this code, but this is just LLVM IR code. So what are the first things that strikes to your mind when you look at this code? Well, first thing is it looks assembly-like. And the second thing, there are lots of types interspersed. And then it's SSA based. You see lots of fee nodes when you have like more than one predecessors. And another key feature of LLVM is high-level data types. Like it has first-class structure types, first-class aggregate types, which is a different design compared to other traditional compilers. Okay, and then you access memory using loads and stores, and you also access high-level data types using loads and stores. And the LLVM has a get element pointer, which is a platform-independent way of like doing pointer arithmetic. Okay, now you want to formalize an SSA-based IR. So SSA is generally defined in terms of the domination tree. So if you're trying to formalize SSA-based IR, you need a formal verified domination analysis. So a Vellvm with a verified LLVM framework provides a formalized domination analysis. And the key thing which we realized during this process of formalizing SSA is you need to define predicates using the strict dominators. So even though it was like it's an insight which is simple in retrospect, but we were figuring out was like a hard part which we had to worry about for the last 1 year. And then the next part in formalizing the LLVM IR is how do we handle undef? And what is undef? And undef is the key feature that makes the semantics non-deterministic. Okay? So let me give you a tutorial on undef. So LLVM has this. So in a program, you can have lots of undefined behaviors. And LLVM classifies them into two categories and wants to do aggressive optimizations in the presence of certain kinds of undefined behaviors. And to do this, it defines an undef value. And there's an undef value of any particular type. So it essentially says an undef of a particular type is a set of all bit patterns possible in the particular type. So in this case, there is an undef of type I8. It says the value could be a set of all values which can belong to any bit patterns. So it's a set of all values in the set 0 to 255. I8 is a signed 8-bit integer. So let's say, and then when you have a concrete value 1, it's a singleton value which is just concretely 1. And now you have, let's say you have an operation which is doing a bitwise OR of an undef and 1. So if you traditionally think, okay, it's an undefined value and you're ORing it with 1, it should be undef, right? But LLVM says no. According to the LLVM semantics, undef is a set of all bit patterns from 0 to 255, and when you OR it with 1, the resultant set is set of all values with the last bit set to 1. And okay, so let's this is what the resultant set is. Let's say there's another operation which uses this value, and you are XORing the resultant value with each other. X XOR X should be 0, right? But since X is undef, it's a set of values. And here, an optimization which just does X XOR X as 0, let's say there is an optimization, let's say we define the semantics to be X XOR X is 0, and there is an optimization which is very aggressive and wants to provide a different value to enable other optimizations. So then we will not be able to capture that optimization. That's why modeling undef was crucial to design semantics to handle large number of optimizations. So in this case, like if you just say 0, we will disallow many optimizations, which are allowed by the LLVM suite. On the other hand, the actual correct value here is you need to model x as a set, and which is a set of all odd integers. And then when you XOR it, the resultant set is a set of all even integers. Okay, so the key reason why we model undef this way is because LLVM IR defines it. And this introduces a certain set of non-determinism. And why? Undef can be part of a branch. So now let's say you have a branch instruction which says branch, the branch condition is undef, and then branch to certain labels. And if the branch condition is undef, it's a Boolean value, it can be both true or false. The semantics needs to explore both the possibilities. And the particular optimization may actually choose one of the other paths depending on whatever is favorable. Okay, so using undef in the IR is one source of non-determinism. And LLVM programs also reason about memory. So the reason is there's a load. When you perform a load on a particular address, the optimization writers actually make some assumptions about what the load is going to return. You need a notion of what the memory is going to do. And there are two ways you can go about designing a memory model for compiler optimizations, right? So you can say, oh, x86 or particular architecture provides a particular platform-specific model. And we can go to a platform-specific model. But when you are designing high-level optimizations, you want a model which is independent of the platform, and also you want it to be independent of the underlying memory manager implementation. So how do you design a memory model which is reasonable enough to reason about programs and capture LLVM's load and store behavior without being too concrete about the implementation? And in this case, ComCert, which was designing a verified compiler, came up with a memory model. And being pragmatic, we just reuse ComCert model. And one of the differences here is ComCert's IR has fixed width integers and fixed size data types. On the other hand, LLVM has like I80s, so integers of varying widths and integers of like varying sizes. So we need to extend the memory model to handle all this. And in the ComCert's model, each memory value is a concrete value. Now in the presence of undef, we need to model the possible non-determinism. So the way we model it is we branch out each concrete instances. We simulate each concrete instances being stored to the memory at every step when undef is involved with a memory operation. This is especially true with stores, is to undef being stored to a memory location. And how do we model the memory model? What memory model do we use? So essentially, you have a high-level data type, and ComCert uses a byte-oriented representation, and we need a way to translate this high-level data types into byte-oriented representation. So this induces, like we need to flatten and construct the values from LLVM's types into our concrete memory model types. And this induces a kind of physical subtyping between the high-level types in the LLVM memory model. And also, when you are designing semantics, you need to reason about the kind of undefined behaviors that would arise when you try to access locations from undefined locations, which are not supposed to be accessed, right? So let's say storing a value is a mismatch type is an undefined value. So we need to capture this in the semantics. So to do this, our underlying byte-oriented representation is typed. The memory model is dynamically typed. So it remembers what type was actually stored in a particular location. And when you actually load a value with incompatible types, it would return undef as required by the semantics. Again, this is for the sake of the proofs. The underlying implementation maybe is free to choose whatever memory model it wants to use. And we want to reason about all possible behaviors. That's why we design a memory model which is dynamically typed. Okay? Okay, so how do we, why do we need, like, okay, so there are two questions. One, okay, we have modeled memory, and we have modeled undef in some reasonable way. And what are the sources of undefined behaviors in general programs or in LLVM IR programs? So just to enumerate all the possible cases, the few of the undefined variables are, undefined behaviors are accessing from uninitialized locations, accessing uninitialized variables, loading with mismatch types. You load from the padding and stuff, then accessing like invalid locations, accessing freed pointers, accessing out-of-bound locations, and calling indirect calls with mismatch types. So among these, if you classify these undefined behaviors into two categories, so there are certain undefined behaviors which actually crash the program, and there are some undefined behaviors which define like different results on different executions. The compiler optimizations are generally meant to preserve the semantics of the original program. If the original program did not have undefined behaviors, the optimized program should not exhibit any undefined behavior. And the set of behaviors exhibited by the optimized program should be a subset of the optimization behaviors exhibited by the resultant program. And the compilers are generally very conservative about introducing undefined behaviors. And LLVM follows the same path. But if there are some undefined behaviors in the program, LLVM wants to be more aggressive. And that's the whole reason for using undef. So LLVM classifies these undefined behaviors into two categories. One, which provide target-dependent results, and the other, which cause the program to crash. And for the first category of variables, it uses the undefined value, the undef. On the second category, it's like the undefined behavior. And the compiler does aggressive optimizations in the presence of undefined values. Okay? So LLVM IR semantics says that it's SSA based, we need to model memory, and we need to model undef. And to model undef, we have a set of values. And we formalize it as a small step semantics. It essentially relates a set of program states to a set of other program states. So the key takeaway is, since there are undef values, and any transition could non-deterministically go to multiple places, like especially in the presence of undef with a branch. So the semantics is straightforward, nothing to worry about. The only thing is the non-determinism is the key thing which needs to be addressed. Okay, so to reason about undefined behaviors, like we need to say an optimization did not introduce any undefined behavior, and it preserved all the behaviors in the original program. We need a way to model undefined behaviors. And the way we do it in the semantics is by defining a stuck predicate, a stuck judgment, which says that these are the possible ways the program can go wrong. And in the semantics, once we have this, we prove that the semantics is sane. If you start from a well-formed state, you can either take a step and go to another state, and the resultant state is also well-formed. Otherwise, if you start from a well-formed state, you either terminate or you get stuck in one of the well-defined stuck states we have already seen, or you always take a step. So this is just to prove that our semantics is sane and works well. Okay, so this was all the semantics part of it. Now the next question is, how do we interface with actual LLVM tools? And how do we even say the semantics is reasonable? To do this, we formalize the semantics in the proof assistant, and then using the semantics, we extract an interpreter. And to do the extraction and do the interpreter, we use the deterministic semantics, where we instantiate every undef with a 0. And then we compare, the LLVM has a reference interpreter, and it has a test suite. And we compare the LLVM reference interpreter's results and our extracted interpreter's results, and compare if they produce the same value. And in almost all the cases, we produce the same value. So this provides some guarantee that our semantics is reasonable and usable to work with LLVM programs. And the next question is, can we actually use it to prove instrumentations and verify compiler transformations? The first step is we have been working on a memory safety transformation. Let's prove this. Let's build a verified memory safety transformation. So in PLDI 2009, we had a memory safety transformation. The essentially C has two kinds of memory safety errors: accessing a memory location beyond the region it legally beyond the region the pointer can legally point to is a buffer overflow, and SoftBound is a transformation which detected buffer overflows with a reasonable overhead. And one of the key features of SoftBound was the semantics were defined on the LLVM IR. So we said, like, okay, take your program, rather than doing your instrumentation either the source code or on the binary, let's do it on the compiler's intermediate representation. And since LLVM's intermediate representation has some nice features such as pointer identification, you can do this on the intermediate representation. And you can leverage the existing infrastructure to do this, and you can reduce it with, you can do memory safety transformation with a reasonable overhead. Let me give you a quick overview of what SoftBound is so that I can describe how we actually go about proving it. Essentially, the invariant is like you maintain base and bound metadata with every pointer. So in LLVM, a value can be either resident in registers, since it's SSA based, or it's resident in memory. For any pointer that's resident in registers, which is temporaries, the metadata is also created to be resident in temporaries. And when the pointers are involved in GEP, which is pointer arithmetic, you just copy the metadata. And before a load or a store, you check whether the pointer being dereferenced is within the base and bound of the region being so the pointer is within the base and the bound, so that you don't have a spatial safety violation. And one of the key features of SoftBound was how do you maintain metadata for pointers in memory? So an alternative would be to change the representation of the pointer into a fat pointer, but this would break the memory layout compatibility and cause problems. So SoftBound decided to maintain the metadata on the side in a disjoint metadata space. And now the key thing was how do you provide the mapping from pointer to the metadata. So you can read the PLDR paper for more details. So, but the key thing here is like the disjoint metadata is maintained on the side. And the key invariant SoftBound works on is the metadata can never be corrupted by any operations on the pointer. You can have an arbitrary cache. The arbitrary cache just munges the pointer values, but the metadata is always consistent, and since the checking is based on the metadata, you provide spatial safety. So since we had designed this, now how do we use the LLVM semantics to verify SoftBound? That was the question we set out to ask. So we designed the SoftBound instrumentation using the semantics what I had described in the last few minutes, and then we are using the extraction mechanisms. We extracted a SoftBound completely from the proofs. And then this SoftBound actually works with the LLVM infrastructure, transforms code, and is much more robust than the C++ version which I had designed like a few years ago. So what are the things we need to model to actually design this? So we said like there are undefined behaviors that a program can exhibit. And SoftBound prevents one of the undefined behaviors, which is the program performing a spatial memory safety violation. So we define a special predicate which says, oh, the program is actually trying to incur a spatial memory safety violation. So when you have like a SoftBound specification, you say the program with a program which is instrumented with SoftBound will never experience spatial safety violation. There are two things you need to enforce. One, given a program state, if the program is transformed with SoftBound, the transformed program should not experience any spatial memory safety violation. And the other thing is the resultant program should preserve all the behaviors of the original program. And this is what the judgment is trying to do here. Okay, so what was the intellectual contribution of doing the SoftBound stuff with the proofs? In the course of the writing the proofs, we discovered that like the original SoftBound, which assigned undef base and bound for a pointer which was undef. And if you recall, undef is a set of values. If you provide undef base and bound, it could be any set of bit patterns, any value from 0 to any value in the 64-bit integer set. So you're arbitrarily manufacturing base and bound. So the working on the proofs actually enabled us to reason about this and provide the right base and bound. And similarly, when the pointer was null, we were actually setting the base and bound wrong. And also the next question is, okay, proofs are all nice. When they actually operate with real world code, do they actually perform as good as the C++ implementation? And in this code, we are showing the overhead of the program transformed by SoftBound. So, and transformed by the C++ version of the SoftBound, and then transformed by the OCaml version of the extracted SoftBound from the proofs. And the highlight, since these are overheads, the lower bars are better. So the key thing to take away is, on an average, both the extracted SoftBound written in C++ and the version which is written from the proofs have the same overheads. And the C++ version has a lot more optimizations. We have engineered it to work a lot more better, has slightly lower overheads. So the question is, there's a value in trying to prove your instrumentation and verifications with a proof assistant. So you have more assurances about correctness. And it also performs reasonably well with existing code. And in the course of this effort, we also made the actual instrumentation more robust, and we came up with various design techniques which made the code modular and easily operable with a real world code. So in general, like, we found that writing verified optimizations actually forced us to think mechanisms to make code modular, code more correct, and in general more robust than ad hoc C++ code which I used to write earlier. Okay, now I'll give you like, okay, we just defined semantics for LLVM and just proved that our semantics is correct with our own instrumentation. How do we use this semantics, whatever we have defined, and prove an existing optimization? And if you are building a verified compilers are meant to give you performance. And writing proofs takes time. And where do you spend your time in writing a verified optimization? So to do this, we need to find the optimization which provides the most benefit so that we can design a verified optimization, right? Okay, to do this, we took spec benchmarks and we ran the code without any optimizations, which is LLVM 0. And then we ran LLVM 01, 02, 03, 04, 05, and with various combinations of the optimization. In general, so LLVM 03 sped up your programs over LLVM 00 by around 100%, 80% for this set of benchmarks. And 01 almost got as much benefit as 03, and it sped up the program by 77%. And 01 runs 68 optimizations. And okay, so which optimization among the 68 optimizations actually provides you benefit? So we found that LLVM's mem-to-reg optimization, which promotes stack allocated variables to temporaries, provides you 70% of the 70% speed up. That's most of the benefit you would get by running 01. So if you are building a verified compiler, the next possible step is let's build a verified version of mem-to-reg, which is SSA construction. So mem-to-reg is one of the optimizations which has the maximum possible benefit. So this is again a work in progress. If you want to know more, talk to me after the talk. But again, just to give you a flavor for what mem-to-reg does. So you have some C code where you're like just assigning x equal to 0, and you're checking y is greater than 0 and setting different values on this. So LLVM transforms this code, the front end transforms this code into trivial SSA. So it transforms this code into trivial SSA by just creating allokas and doing operations on it. So you have a load and a store and an alloka. So there is no SSA variables. And then uses mem-to-reg to convert it into the minimal SSA form. So the common algorithm used by mem-to-reg is called the Wegman-Zadek Citron algorithm, which uses domination frontier and places minimal phi nodes. But we initially started out to prove this, and we figured out that the intermediate stage breaks the SSA invariant. So now if you are designing proofs, like if there's an intermediate stage breaks the SSA invariant, this is during the renaming, we couldn't come up with the proofs easily. So we designed a new version of mem-to-reg, which maintains the SSA invariant at each step and still transforms real world code. And the bottom line is the verified mem-to-reg almost gets the same performance as the C++ mem-to-reg which is present in the LLVM suite. So to summarize, like I described the semantics of the LLVM IR. We showed that the semantics is useful to reason about optimizations and instrumentations. And I think getting developer involvement is very useful. And programmers, compiler writers generally think about performance and compilation time. They don't think about verification. And in thinking about verification, how to prove your optimizations is a good step to make it robust. I think it's the Vellvm is a foundation for building a future verified compilers. Thank you for your attention.
We have time for a few questions.
Hi, John Crizzle from University of Illinois. One question I had is, did you measure the performance of the actual transformations, how long it actually increases compile time?
Okay, so we have some initial results on the compilation times. Since this is like a different infrastructure, uses OCaml, we do slow down compilation by a factor of 2 or 3, and depending on what algorithms you actually do to the extraction and the parser and the printers, the slowdowns can actually vary. So compilation time, we are slightly slower. It depends on what slightly is, but than the actual LLVM C++ implementation.
Okay, thank you.
I'm Flash Sherd, and I'm testing the compiler at Apple. And going a bit beyond what you did say to what you didn't, did you try to verify any modules and fail? And should we worry? Any signs of bugs in an inability to verify a part of the code?
Okay, so we did not find bugs in existing optimization. So that was not our goal to start with. So our goal was to given there is an optimization. So do we even say this optimization is correct or not? So the underlying heart of these optimizations are correct because they use well-known algorithms. Like Wegman-Zadek's algorithm is prone to be the specification of the algorithm is shown to be correct by Wegman and Zadek in their papers. Now there's an implementation which is written by this LLVM community. And the implementation writer makes lots of things, makes lots of choices. And why are these even correct? So that was the goal. Our goal was to show that the actual implementation faithfully implements the original algorithm. And so since we proved a different version of mem2reg, we haven't completely proved the existing mem2reg yet. So we haven't found any bugs or slight discrepancies in the LLVM's mem2reg implementation. But that's a good question. How do you even actually use a proof and say the correct implementation is correct or wrong or slightly does different things? So what happens when you try to prove is we find, oh, this is not provable. This could mean the implementation is wrong, or we haven't designed a proof technique which could capture this. So it could be both ways. So we don't have a concrete answer for that.
Right, as sort of a self-test of your methodology, you might try looking at some optimization implementation that has had a bug, and I'm afraid there are some, and then see where your methodology fails. That would at least be interesting to me.
For example, we designed a couple of translation validators. Essentially, you're taking two pieces of code, and we had a translation validator which was completely buggy, and then we actually tried to prove it. We couldn't prove it because it said it failed the semantics. We are sound in that regard. If there is a bug in the validator or optimization, we would say, oh, you cannot prove this. But this doesn't rule out the other way, right?
Right, but it might be interesting to look at the modules that fail.
That's an interesting direction, yes.
Thanks.
Thank you.
Actually, I also have a question. So when you run the verifier, is there a requirement on how big or how complex the path you try to verify? I can't remember the mem2reg path isn't that complex. It's relatively short. So if I give you a much longer or more complex path, will your verifier be able to finish in a reasonable amount of time? So there's a difference, right? mem2reg is around 2,000 lines of C++ code. And it's not complex in whatever, but it uses all the cases of the LLVM semantics. If you read our Popple paper, let's say when there is a alloca from an initialized location, and then the store of a value into an alloca into that alloca location, and then there's a return of the loaded value. So the LLVM optimization was just returning 10. There is input code was load from uninitialized alloca, store some concrete value to that alloca, and then return of the loaded value. So LLVM optimization was just returning 10. So why is you need to reason about why is this even correct? So the mem2reg makes some assumptions about the semantics. So you need semantics, and then when we are not verifying it. There's a one-time intellectual effort in building a verified instrumentation, and then once this is done, and once you trust the underlying logic, which is used to build the verifier, build the verified optimization, then the code is you have an implementation which comes with you don't need any extra verification effort. So the key part is actually building a verified optimization. Yeah.
I don't know whether I'm answering your question clearly.
Yes, right, okay. So are there any more questions? Okay, let's thank the speaker again.
Thank you.